Okay, so as you see, and so when we are doing that, so we are taking a representation, then we select a block here, then we select inside another block here, then inside we select another block. What we are doing is we are taking a representation here, then we are following a path here, then we are following down the path. Okay, so this is I, J, K here. So, okay, so each of these paths here will correspond to a certain block inside my matrices, a certain family of matrices, say a certain block. And if I go down, well, in the end, I get an irreducible representation of the trivial group. So it must be a vector or a one-dimensional subspace. Okay. So in the end, when I do all these decomposition, what I see is that for each of these paths, which go in the branching graph, I will get a vector. Okay, and they will form a basis of the for each path. Let me call it omega in the graph. So the path go down along the graph from one of the points here to here, or go up if you want. It's equivalent. I obtain a vector, or a one-dimensional subspace if you want, V omega. And these V omega, they span the space. Okay? Because in the end, what I obtain is I obtain a decomposition of the irreducible representation into irreducible representation of this group, which is a trivial group, so it must consist of a sum of one-dimensional subspaces. Okay. So this algebra is so if you want, in the end, what you will obtain is the algebra generated by all these centers here will be given by the algebra of diagonal operators in this basis, which is V omega. Okay, so what I claim is the following. So the algebra GZ consists of all operators which are diagonal in the basis V omega. Okay, where omega is a path in the group in the branching graph. Okay. So it is a maximal abelian algebra, because it is the algebra of all diagonal operators in some basis. Okay, so it's a maximal commutative algebra in the group algebra. And if you look at its restriction in each of these blocks, okay, here it's a maximal abelian algebra also in each block. Okay. Okay, so now there is a little lemma. The lemma is that if I look at the algebra generated by the center of Sn and the center of Sn minus 1, so this algebra, this is the same as the algebra generated by the center of Sn minus 1 and Jn. In particular, it is equal to the commutant of Sn minus 1. So why is it true? Because certainly the elements here commute with Sn minus 1. Elements here commute with Sn minus 1. So there is certainly an inclusion which is here. Okay? But on the other hand, so these elements here, they belong to this algebra. So I just need to prove that Jn belongs to this algebra. But Jn, it is just the sum of all transposition in Sn minus the sum of all transposition in Sn minus 1. Okay? It's just the sum of all transposition in Sn which don't belong to Sn minus 1. Okay? So it's a difference of two elements in these algebras. So certainly it belongs to this algebra. Okay? So this proves that we have this equality here. And now you can, so in this, when I look at the sum of these algebras here, I can replace Z of Sn by Jn in the sum. And now I can do by induction, I will replace, I will use this lemma again with Sn minus 2 and Sn minus 1, and so on. And in the end, what I get is that this algebra is also, okay, so it's maybe, okay? It is the same as the algebra generated by all the Ji, okay? So this means that the Ji, they are diagonal in the basis V omega. And moreover, since they generate the algebra, I can distinguish all the V omega according to the list of their eigenvalues corresponding to the Gi. Okay? So this means that to each omega, to each path, the list of eigenvalues, say A1, An, so this means that Ji V omega is equal to Ai V omega. Okay? And this is a one-to-one correspondence. Because if assume that some omega, 2 omega will correspond to the same list of eigenvalues, then I will not be able to distinguish the vectors, the two vectors, using just the operators Gi. This means that they will. Okay, so this means that the algebra Ji will not be equal to this maximal abelian algebra. Hmm? Okay, so you can parameterize your vectors either with paths in this graph or with the list of eigenvalues. Yes, yes, okay. There is some, not every sequence of numbers can appear, of course. You have lots of constraints. For example, the A1 is equal to 0 because the first J1 is equal to 0. So you have lots of constraints. And we will explore these constraints and see that we can actually completely describe this. And okay, so in order to do that, so now we are going to guess, to do some guesswork. So I'm going to give you the answers that we will check, but now the answer is not that difficult to guess. So here you see, what I say is that we have as many elements as we have partitions of n. Here we have as many elements as we have partitions of n minus 1. Now we have a certain number of edges between them. And what I said is that these edges, the number of these edges is just the dimension of the commutant of Sn minus 1 into Sn. Okay? And as I said, they are parameterized by, oh, that's extraordinary, they are parameterized by pairs of partitions. What a coincidence. Okay. So the guess is that, well, this parameterization is a nice one. And actually, the graph consists, the branching graph consists of looking at partitions here and looking at partitions mu, which differ from lambda just by one box. Okay? And this is a branching graph. So there will be an edge between two partitions exactly when we are in this situation. The partition lambda is a big partition like that, and mu is a smaller partition with one box erased, one of the corners of the partition lambda erased. Okay, so this is a reasonable guess to make, given what we have seen, that actually at least the numbers coincide. I mean, the numbers above here, and the number of elements here and here coincide, and the number of edges coincide. So it's a reasonable guess. Okay. But now what we have to understand is what are the eigenvalues of the Justice-Murphy elements. Okay. So for this we'll make a small guess again. So for this we have to look at the graph. So let us assume that the graph is. So I write my partition in the Russian style as I mentioned in the beginning, so I make a rotation. So here is the first one corresponding to the group S1, and in this case, J1, I know it is 0, so I put a 0 here. It corresponds to the eigenvalue. Okay? And then, okay, I have two. So my graph starts like this. I want to add a box to my partition, my first partition, so I can add a box on the right or on the left. Okay? And the list of eigenvalues. So the first element J1 is equal to 0, and J2 is equal to 1, 2. So in any representation, this element will have eigenvalues +1 or -1. Okay? Okay, so, well, I guess I could put -1 here and the 1 here. Okay, why not? Then you have to, when you continue building this graph, yes?
In the Russian representation, which are the paths?
What? In the?
What's the direction in
it doesn't matter. I mean, it is just, these are what I claim, these are the same graphs, but it has nothing to do with the group structure, actually. Here it is connected to the group structure. This graph tells you, the graph which is here, where we have these pairs here, tells you if you have a conjugacy class in Sn, how does it decompose into classes under the action of Sn minus 1. So this is what the graphs tell you. And this graph tells you have a representation, not a conjugacy class. How does it decompose? And the miracle is that there should be the same graph. It's a miracle because for general groups, there is no reason why this should happen. Actually, it doesn't happen like that in general. In general, there are multiplicities, and if you take two groups, it's okay. So the fact that it works for this group is a kind of special. When there are you could find other series of groups for which this would work, but I mean, it's in general for arbitrary finite groups doesn't. In particular, if you want to find you have a group G, you look at a conjugacy class C. And you want to look how this conjugacy class is decomposed under the action of H. It is decomposed into classes, but there is no reason these classes should match with some conjugacy classes of H. This is very particular to this situation. In general, there is no reason. So in general, we cannot build a graph like that for general groups. I mean, so it's really something special here, which is happening. So here, we expect to have this. And now, well, as I said, there are three representations of S3 that we saw in the first lecture. So in one of them, so the eigenvalues are, so say J3 is, so if we look at the list of eigenvalues in the sign signature representation, the eigenvalues are 0, -1, -2. Okay? And I have the list here. And in this representation, which is a trivial representation, I will have 0, 1, 2. And in this representation, you can check, I mean, this is a computation that will have -1 and 1. Okay? So from this, it's again, we will make a guess. And we'll make a guess that, so what I say is that every path in this graph, so it is a graph of partitions where you have these edges between two partitions where they differ just by one box. Okay. For every graph for every path in this graph, going from this bottom partition to some partition above, I will associate a list of eigenvalues, and my guess is that the eigenvalues they are just given by the following. So I give you an example. Again, it's a guess, but we will check that it works. So suppose you have say this here. Okay, so you can. So what does it mean finding a path which goes from this here to this here? This means that I put a number on each of the boxes each time I add a new box. So I start with 1, 2, 3, 4, 5, 6, 7, say. Okay, that's one way. And what I get here is well known. It's called a standard tableau. So it is obtained by just putting numbers from 1 to n in the box here, so that they are increasing along the diagonals. Okay, it's called a standard tableau, and it is equivalent to give a standard tableau to give a path in this graph, which goes from the first box to the final partition, which is here. Okay. And now, if I have a standard tableau, well, okay, what I look is the following. I will look at so I put numbers here, which are called the content of the like that. Okay. In each box, I put an integer which corresponds to the, if you want, the projection on the x-axis of the box. Okay. What is the coordinate when I project on the x-axis? So here I got zeros. Then on the right, +1, then on the left, -1, -2, +2, etc. And what I claim is that the sequence of eigenvalues corresponding to this tableau will be, well, I will first get a 0, then I get a +1, then I get a -1, then I get 2 here, and then 0, and then 1, and then -2. Okay? And what I claim is that, well, this gives me a complete description of a basis of, say, an irreducible representation corresponding to this partition of the symmetric group, a basis together with all the eigenvalues of the Jn. This is not enough to say how all the symmetric group will act, but we will see that we even can get that using some little algebra. Okay, so now I'm going to show you that what I'm going to show is that what we have proved is that every so irreducible representation. So in every irreducible representation of Sn, I can find a basis V omega indexed by A1, AN. Okay. So I don't know yet that my graph is the graph I described. I told you that it is a reasonable conjecture, but of course I have not proved that. But what I know is that, on the other hand, is that these numbers, they completely characterize the basis. Okay, I can index a basis by the sequence of eigenvalues. So it's a sequence of eigenvalues of V omega of Ji on V omega. Okay, so V omega is a common eigenvector, all these operators, with this sequence of eigenvalues. So of course, there are lots of constraints. In my description here, you see that not, of course, in particular here, I only have integer eigenvalues, and not every sequence of integers can appear. I mean, there are lots of constraints because of the construction of the eigenvalues. But what? Yes, a path. For example, the path here, it will be just this one. So you just write, okay, 1, 2, 3. You look at the partition you have constructed with the numbers from 1 to k. It is a partition, and it is where you are in your path. Okay, the path goes like that. Okay, so it is certainly a path in the set of partitions. Okay, and so on. Okay. you see there is a bijection between standard tableau and paths. I add a box each time, so it's I go up a level, and according to my graph, because I said the edges in the graph correspond exactly to this operation or adding or erasing a box. Okay. So how are we going to prove that? Well, we are going to prove that there are many constraints on the list of eigenvalues, and that these constraints correspond exactly to all the possible sequences of numbers that we obtain by looking at standard tableaus. Okay? So for this, we will look at a sequence, A1, AN, and I will look at a sequence of consecutive eigenvalues and see what two eigenvalues or even three eigenvalues, and see what constraints I have on a sequence of eigenvalues which occur in my sequence. Okay. So for this, we remark, so this is the eigenvalue of ji and of ji plus 1. Okay. And now I remark that there is an element Si, which is a transposition between I and I plus 1. So Si commutes with G1, etc., up to Ja minus 1, and with Ji plus 2, Jn. Okay? So in particular, if I look at a sequence A1, AN, I look at these two numbers, okay? I can forget about everything which is on the left and on the right if I look at the action of just these three elements, Ji plus 1, and Si. Okay? Because they will not change anything on the left and on the right, because they commute with all these operators. So they will not, they will leave invariant all their common eigenvectors. Okay? So I can concentrate on eigenvectors on looking at what happens here. And now there is a very nice relation, which is that you can see, Ji plus 1. So it is I plus 1. Yes, it's I plus 1 plus the sum of, say, k I plus 1 from k equal 1 to I minus 1. Okay, so this is, if you want, Si plus. And this looks very much like Ji, except that here I have I plus 1 instead of A. But, okay, what I can do is I can make just a conjugation. And this has the effect of just replacing in Gi the I by I plus 1. Okay? So there is this very simple relation between these two operators, these three operators. Okay. And now if I want to understand the action of these three operators, you see that this relation does not depend on I, actually. It is the same relation for every I. Okay? And so what do I know about the operators in some irreducible representation? I know that this is a self-adjoint operator. This is a self-adjoint operator. There are three self-adjoint operators. And they satisfy the following relations. So S squared, let me abstract this in the following way. I have a triple of operators, say X, Y, S. Let me call X, Y, S, because actually the relation don't depend on I. So I just call it X, Y, S. So S squared is equal to 1. XY is equal to YX, so they commute. And we have this relation, which is X is S plus SYS. Or I can rewrite it also S equal 1 plus YS, or XS is equal to 1 plus SY. Okay? Any of this relation is equivalent to the others, just because S squared is equal to 1. So I have all these relations. So now I want to understand what happens when I have a vector V. I suppose that xv x has some eigenvalue. So V is an eigenvector. I suppose I have three operators in some space which satisfy those relations. So xv is equal to lambda v. Yv is equal to mu v. for some eigenvalue. Okay. And what I claim is that if I have a common eigenvector to x and y, claim the space generated by V and SV is invariant under the action of S, X, Y.
Now you're taking three operators which behave
Yes.
three equations.
Yes.
And you are claiming that x and y have the same eigenvectors.
No, I say, suppose I have some eigenvector, a common eigenvector, x and y commute.
So that's an hypothesis.
That's part of the hypothesis of what I make on the operator. I have a triple of operators which satisfy this. Okay? If I assume also they are self-adjoint. Okay? So if I look at any representation, any triple of operators which satisfy this relation, I can find a common eigenvector to x and y because they commute. Okay? And then, okay, and that's all I say. I can always find in some space a common eigenvector. And I'm looking at this eigenvector. For example, this is what I get here. I get these three operators, and I got a common eigenvector to gi and gi plus 1. Okay? Which is the vector v omega, corresponding to this sequence of eigenvectors, eigenvalues. I say there is in my representation of Sn, there is a basis which indexed by all these sequences of eigenvalues. Okay? So in particular, if I restrict to the algebra generated by gi, j plus 1, and si, so here I have a common eigenvector. And OK, I can forget about all the other eigenvalues because everything commutes, and so they will not be touched by what I'm going to do. OK, they will remain all the action of j, ji plus 1, and si will not change the fact that I'm still in the eigenspace corresponding to the other eigenvalues of these other operators, because they commute.
The space is generated by
Eigenvectors.
you're taking the space generated by the eigenvalue on the left and on the right.
No, what I'm saying is that there is a space, say V, indexed by A1, A, I minus 1, A, I plus 2, an, which is the space where these vectors have the eigenvalues, these operators have the common eigenvalues which are given by that. It is a certain space. Okay? I don't know what is its dimension, but it is a space. And certainly this space is invariant under these operators because they all commute with these operators. So if I have a common eigenspace and I have an operator which commutes with everything here, certainly it will live invariant this operator. This space, sorry. Okay? So let me go to the abstract situation. I just have this free operator, x, y, s. Okay? I suppose that I have a common eigenvector. Then what I claim is that this pair of vectors, they generate a space, and this space is invariant under the action of these three operators. It is clear for s, and for x and y, it just follows from the, okay, just a simple computation. Actually, if you look, so there are several possibilities. V is equal to SV, V is equal to minus SV, or V and SV, they generate a two-dimensional space. Okay? So in the first case, is V is equal to SV. So this implies that, so if V is equal to SV, so here I have x equal 1 plus y, so lambda is equal to mu plus 1. The other possibilities is that lambda is equal to mu minus 1. Well, actually, here I have an equivalence. I'll show you why. Because if lambda is equal to mu plus 1, suppose I have my vector v, and suppose that v is different from sv. Then I can look at the vector v minus sv. And you can see that v minus sv will be an eigenvector because of all these relations, and because of this relation, v minus sv will be an eigenvector of x and y. But it is not possible because x and y are self-adjoint, so this should be orthogonal to V. Okay? And S is okay. So this is V times V minus SV times V. And this cannot be equal to 0 if S, unless V is an eigenvector of eigenvalue 1 of V. Okay, because S is unitary operator. Okay, so okay, if you don't follow the argument, it's a little simple, very simple argument to tell you that these things are just equivalent. Okay, so this means that if here these two elements will differ by 1, if and only if they are V is an eigenvector of Si. Okay, but if it is not true, then in the basis VSV, X will be given by this matrix, and Y will be given by this matrix. Okay? In the basis given by V and SV. So this is very simple computation using these relations. Okay, you can easily check that in this basis they are given by that, and of course S will be equal to this operator. Okay, but now look, if lambda is different from mu, if lambda equal mu, so I claim that it is not possible. This case is not possible. Lambda equal mu. Why? Because X and Y are supposed to be self-adjoint. If they are self-adjoint, I can find a basis in which they are diagonal. Okay, and this means they are multiple of the identity, and this is not the case here. Okay, so they have a bad Jordan form. So certainly this is not possible. Lambda equal mu is not possible when X and Y are supposed to be self-adjoint. Okay, so certainly lambda will be different from mu, and there will be so X and Y will be, and you can check that there will be another eigenvector. So there will be a basis, VW, in which X has the form lambda like that, and Y has the form mu 0, 0 lambda. What? I claim that there exists W in the space generated by V and SV. Just take these two matrices and find a common eigenbasis. That's all. Yes. W is a combination of V and SV that you can find out easily. I mean, you do the computation. I will not do it here because I will do it wrong. So, so just do it for yourself. Okay. So there is a basis in which we have this. Okay. Okay. So maybe I can write here. Well, in the new basis, S will not be equal to that. It will have another form that you can compute if you want. Okay. Okay. So now I claim that there is okay. Using these considerations, so I will write down a lemma which tells you what I can say about the sequence of eigenvalues which occur in an irreducible representation of the symmetric group. Okay? So there are some statements, 6 statements. So the first is that AI is different from AI plus 1. Okay, so this we have seen. It is because X and Y are here self-adjoint. So certainly they cannot share an eigenvalue because of this thing here. The second is if so my hypothesis is that A1, AN is a sequence which belongs to this sequence of eigenvalues which occur in my representation. What I say is that if AI and AI plus 1 differ by something which is different from 1, So if you want AI plus 1 is not equal to AI plus 1 or AI minus 1. Okay? So we are not in these two cases. If we are not in these two cases, you see there is another in the space generated by this the eigenvector corresponding to this eigenvalue, and it's imaged by SI. There is some vector which has the opposite eigenvalues. I mean mu and lambda. They are exchange. Okay. So this means that if in a sequence like that, if two neighboring elements they differ by something which is not minus 1 or plus 1, I can exchange them. Okay? And okay, so it is a common eigenvector of all the GI. Okay? For the moment, I don't speak of paths because I don't know that I am in this graph. But I can show you nevertheless that if you look at my picture here, so suppose at some point, okay, so at some point, say the graph up to time or to corresponding to SI is here. So suppose that the I is here and the I plus 1 is here.
I cannot do that.
Hmm?
It must be on a corner.
Oh, sorry, yes, it must be on a corner, sorry. Yes. So there is a corner here and a corner here, and they differ by more than 1. Okay? They are so I had my path. I added a corner at step E, and then the corner at step I plus 1, and they differ by more than 1. Then I said that actually I could have put this one first and this one after. This is the statement here, which is here. Okay? Okay, so there is another statement, which is, so this I have proved, and if AI is equal to AI plus 1 plus or minus 1, then the vector V satisfies SV equal, so minus or plus 1 V. Okay? This is the statement which is here about these operators. Tells me here the self-adjointness is important to get this condition because, okay. So if AI is equal to AI plus 1, plus or minus 1, so this corresponds in my picture here to the case that, for example, I have put here I and I plus 1, you see? Then in this case, I cannot put the I before the I plus 1, the I plus 1 before the I here. Okay? Hmm? Yes, SI, sorry. And V is the, okay, this corresponds to this. It's the eigenvector corresponding to this eigenvalue list, which is here. Okay. The fourth statement is that so say AI minus 1, AI plus 1. So if I look at this, the number, if AI occurs in my list, either AI minus 1 or AI plus 1 has occurred before in my list. Okay? What I claim is that if in my list, if I look at the eigenvalues before AI, either AI minus 1 or AI plus 1 has occurred. Okay, so what does this mean? This means that you cannot, so for example, you cannot get this before at this step because you cannot go too far. Okay, you need to be above your diagram at step I. You can move at least at most once on the right or on the left when you move. Okay. Yes. Okay. Yes, it implies you have only integers. And okay, so how do you prove this? Well, you prove this by induction. So you use what I said that you can always, if AI, so either AI equals AI plus or minus 1. In this case, there is nothing to prove. But if AI is different from AI plus or minus 1, sorry, I'm going too far. Minus 1 plus or minus 1. So if the preceding differs by 1 or minus 1, there is nothing to prove. And if AI is not equal, then I can certainly the sequence AI minus 1 belongs to my set of eigenvalues, to my list of eigenvalues. I can, as I said, I can always transpose them if they differ by more than 1. Okay, as I showed in my picture. And then by induction, I can assume that it is true before, and then I get the property. Okay? Induction on I, by induction on the length I. And you have to check that it is true, and you have to check because A1 is equal to 0, and A2 is equal to plus or minus 1. That's, you have to check. You start with that, okay? And then you check, and then you do induction on the I, which is here. And so here, by induction, here I have a list of lengths I minus 1. So in my list before, I certainly had one of these numbers, AI minus 1 or AI plus 1, which occurred before. Hmm? What did you say?
A2 equals plus minus 1. You don't need to divide by lemma.
This, you mean?
No, the fact that
A2 was
A2
not equal to plus minus 1. It cannot be 0. It cannot be different.
No, but A2 you compute. It's just eigenvalue of a transposition. I mean, it cannot be anything less than plus 1 or minus 1. Just don't...
I agree, but it was not even necessary.
Okay, maybe, okay, maybe. Okay, and the last, the last step is,
Wait,
yeah.
I don't. The second statement.
Yeah?
I don't see how.
It relies on this computation, which is here. I say in the space generated by V and SV, there is another eigenvector, and its eigenvalues are the one but transposed. You see the vector W, so the vector V, its eigenvalues are lambda and mu, and the vector W, its eigenvalues are mu and lambda.
Okay, but then
So I say in the space,
this is about possible sequences of eigenvalues.
yes.
I don't see how this special computation tells
No,
us that.
in my space, I have a vector V, which this sequence of eigenvalues. I can always apply SI to V. Because it is in a representation by hypothesis. I mean, I need to use that at some point. I am in a representation of the symmetric group, and certainly all these relations are satisfied. And so SIV, it exists. It is not, V is not an eigenvalue because of the preceding argument, and then this space is two-dimensional, and in this space there exists another vector which has eigenvalues switched between I and I plus 1. Okay? So this is the argument. Okay? Well, there is a final statement.
You said 6 initially.
Yes, but no, the 6 is this one, which is trivial. Okay, so. And what I claim is that if say AI is equal to AJ, with J strictly smaller than I, this may happen. So for example, this may happen, so say you have some J here, and you have some AI which is above. So this means, you look at the picture, if something like that happens, that it means that these two must have happened before J. They must have happened between J and I. Okay? So this means, then, AI minus 1 and AI plus 1 belong to the list of between J plus 1 and AI minus 1. Okay? What I claim is that in the list of eigenvalues between J plus 1 and A minus 1, this number occurs and this number occurs. It's AI plus 1 or AI minus 1. Okay? So you see, you see, what I claim is that if I occurs here and there was J before, then certainly these two boxes must have been present in the list. Okay, sorry, I write it above. So it's AI minus 1, AI plus 1. It's in the list between AI plus 1 and A. It's not much better, but okay. You understand what I mean? It's in the list of the eigenvalues between I plus 1 and J. Sorry, it's J plus 1 and I minus 1. Okay? Okay, so this is the first statement. Then, okay, it's a bit more tricky, so I leave it as an exercise. And you have to, basically, you have to prove that, well, it's by induction, but there is a trick. So induction on I, and certainly, I mean, you can move everything. Suppose you have AI, so you have AI here, and AI occurs here. Okay, so if you do it by contradiction, suppose that neither if neither of these two AI minus 1 and AI plus 1 occurs in the list, then you can move this one by my lemma. I can make transposition and move it here, but this is not possible because two. So there must be some I plus 1 somewhere, or maybe AI minus 1. Let's suppose AI plus 1, for example. Okay, so okay, and I can assume that this one is maximal. Say there is no other on the right. And also, okay, and if there is no, I do a short argument. I mean, you have to be a little more careful, but basically, if there is no other AI, if there is no AI minus 1, then you can have a sequence like that. Okay, and this is not possible because then Si. Say Si minus 1 would have eigenvalue 1, and Si would have eigenvalue 1. No, sorry, minus 1. You go up and you go down. So the eigenvalue is minus 1 here and plus 1 here. Okay? By what I said here. Okay? But this is not possible because Si minus 1 to the third is equal to 1. The product of two transpositions like that is a 3 cycle. So if I put it to the third, it's equal to 1. But then the vector, and you see if it is an eigenvector, it cannot be simultaneously 1 for this one and minus 1 for the other, because minus 1 to the third is equal to minus 1.
Small fact is at the basis of the fact that standard tableau exists.
What?
This tiny fact is related to the existence of standard tableau.
Exactly. Okay, so so now what remains is that, so I have proved all these properties. Okay, so now what you can check is that using that, you can check that any sequence which satisfies all these relations necessarily is a sequence of successive contents of a Young tableau of some shape. Okay. Moreover, I can, if I have some tableau, I can the action. I know how the SI act on these vectors because it is hidden in this computation which is here. Either I have plus or minus 1 eigenvalues, or I have 2 by 2 matrices to compute, which are here. Okay. Actually, this form it is called Young's normal form. This way of describing the representation. by giving the way the Coxeter generator, so the SI as the Coxeter generator, giving the way the SI are represented in the basis. It is called, so you can write down explicitly the matrices, okay? And in particular, you can see that if a vector V corresponding to some tableau occurs in the representation, you can find by the action of these operators another all the other V corresponding to the same tableau, to the same partition. Okay, because of the lemma, you can do these transpositions, and it's easy to see that any two tableaus corresponding to the same shape are related by a sequence of transposition of I plus 1 as I had before. Okay. But you can always put them in the canonical form when you start like 1, 2, 3, 4, 5, 6, etc. Reading the tableau along the diagonals like that. But just by making transposition. It's not difficult to check. Okay, so this proves that any irreducible representation of the symmetry group has a basis indexed by either Young tableau or sequences like that which correspond to the successive contents of the boxes of a Young tableau. Okay, so there is a basis like that. We can express the SI explicitly in this basis as by explicit matrices. Okay, okay. But now what remains is to prove that they are irreducible and that we have the list of irreducible. But here, the general theory tells us that there are at least, well, there are exactly the same number of irreducible. I prove that all the irreducible has to be of this form. So there are exactly all the irreducible, because they cannot be irreducible, because if then I would not have the right number of irreducible. Okay, I would have less if some of them were not irreducible. The number, okay, number of irreducible representation equal, say, it's P of n. It's a number of partition of n. Okay. Now what I proved is that I have constructed. I said that every irreducible. To every irreducible representation, I can associate a partition like that, and a representation of the symmetry group on the set of on a vector space whose basis indexed by a tableau of the corresponding shape. Okay. Now, all the irreducible representations are of this form. Maybe some of them are not of this form, but this is not possible because if some of them were not irreducible, I would not have the right number of irreducible. Okay. It's a bit, I mean, it would be better to check directly that these are irreducible. Okay, but this argument tells you that you have found them all. I mean,
the irreducible are the diagram. And the tableau, they are
yeah, the irreducibles are the partitions. The set of partitions give you the irreducible, and the diagrams give you a basis, a canonical basis that you can find in your space. By looking the Gelfand-Settin algebra and diagonalizing the Justice-Murphy elements. Yeah? No, I prove that if a sequence corresponds to an eigenvector, then it corresponds to this. It has these properties. So it must correspond to that. But conversely, you can check that if you give yourself for each tableau a basis vector, and you act according to SI, then you have a well, okay, I didn't even check that I really have a representation. I should have checked that the SI satisfies, so for example, the Coxeter relation. But I don't even have to check that because of this number. If it didn't work, I would be. I mean, all the theory would be, the general theory would be false. So, okay. Well, of course, I mean, it would be better to prove directly that your representation is irreducible, but it's a bit tricky. But this tells you don't have anything more to do in order to prove that you have all the things that you need. That's all. Okay? Okay, so in particular, if I have a partition lambda, the dimension of lambda is the number of Young tableaux standard Young tableau that is part in the graph. Okay, and of course, this description also shows you that your graph is what I said. I mean, the restriction, because it's you just need to check that when you restrict your representation to from Sn to Sn minus 1, you see what happens if you have a partition. Suppose you have a partition like that. So it corresponds to a representation of Sn. So what do I need to do in order to obtain a representation of Sn minus 1? I need to erase some box. So it has to be a corner. So either this one, or this one, or this one, or say, okay, this one maybe. Okay, so here there are 4 possibilities. And okay, so when I look at Jn now, the operator Jn is in the group algebra. So its image in this representation, it will have 1, 2, 3, 4 eigenvalues. The eigenvalues will be the contents, which are here. So let me call them x1, x2, x3, x4. So the spectrum of Jn will consist of these 4 eigenvalues. And the eigenspace corresponding to the eigenvalue, say x something, and xa. So the eigenvalue correspond to the eigenspace. So the eigenspace will be an irreducible representation of Sn minus 1, one of the irreducible representations that I obtain when I restrict Sn to Sn minus 1. And it will be given by the one in which I have erased the box. That, say, for example, this one. Okay, so you erase the box, you obtain a representation of Sn minus 1. What I claim is that the eigenspace of Jn corresponding to this eigenvalue is exactly this irreducible representation of Sn minus 1. Okay. And of course, Jn commutes with Sn minus 1. It is exactly equal to the commutant of Sn minus 1. Okay, so it generates with the center of Sn minus 1 the commutant of Sn minus 1. So in particular, it gives different eigenvalues to all the irreducible representations that you obtain by restricting. And okay, so the other remark that I have is that the dimension of lambda is the number of Young tableaux, a standard Young tableau of shape lambda. Okay, so that means the number of ways that you have to put numbers from 1 to n here in order that they are increasing along the lines and along the diagonals. Okay, so I don't know what time is left. Okay, still some time. Okay, then I have to. So we are almost. I mean, we are almost finished with the representation theory of. I mean, for actually what I will need of the representation theory of this symmetric group. Next time we will do the asymptotics. But first I need some very important formula, which is the Hooke formula. So what is the Hooke formula? The Hooke formula is an explicit formula for the dimension of lambda. Okay, so how does it look? It looks like the following. So it is n factorial divided by the product of the hooks of the shape lambda of the partition lambda. So what is this product? Okay, so now you can put some coordinates on your diagram, like I and j, say, and look at a box given by a pair of coordinates. Okay, so here the hook of a box, what I call hij, is the number of boxes which are which go on the diagonals above and on the two diagonals. Okay, like that. So 1, 2, 3, 4, 5. So here the hook is 5. Okay. So now the claim is that the dimension of my representation, that is the number of standard tableaux, or the number of parts in the graph, if you want, is equal to n factorial, divided by the product of these numbers. Okay, so example. Okay, so maybe like that. 1, 2, 3, 4, 5. I'm going to write down the tableaus. 1, 2, 3, 4, 5. 1, 2, okay, so 1, 2, 3, 4, 5. 1, okay. 1, 2, 3, 4, 5. And I think I'm missing one, which is, yes, 1, 2, 3, 4, 5. Okay? So I have 5 tableaux. And now you compute 5 factorial divided. So what are the products of the hooks? I will write down the hooks in the boxes. So here is 1, 2, 3, 4, 4. Here you have 3, and here you have 2, 1, 1. Okay? Okay, so it works. It's not so easy to do. I didn't prepare it. Okay. There are many proofs of the hook formula, but usually many of them use some algebra or some combinatorics. So I will present you now a very beautiful proof, which is probabilist actually. And it is interesting because it will introduce a probability measure that will be very important in the following. Very, very important. So the proof is by induction on n. Okay, on the size of the partition. So define psi of lambda. It's the inverse of the product of the hooks of a partition. Okay? I want to prove that the number that no, let me define the other one. This will be better. The product of the hooks. Okay, psi of lambda. So it's an integer. So I want to prove that n factorial over psi of lambda is equal to the number of paths in my graph. Okay. So what I claim is that so I have to check that this so what I claim is the following. So if you look at your partition, okay, there are some corners, okay? We have been looking at these corners for some time now. Okay. What I claim is that if you look, I'm going to explain. I'm going to explain what is this formula. So I claim, so n factorial over psi of lambda, I want to check this formula. And first I explain the formula, and then I explain why I want to check it. Okay? So this is supposed to be the number of standard tableaux. Okay? Now, take a standard tableau of size n. Then the n will appear in one of the corners. Okay? It cannot appear anywhere else. So let's assume it is in some corner. I call C the corners which are here. So here there are 4 corners. Okay? So the n will appear here. Okay? And what I say is that the number, so if I erase this n, I will remain with a standard tableau of size n minus 1. Okay? So what I claim is that this sum is over all the possible places where the n can occur. Okay? And here it is I assume that by induction, this is a number of standard tableau of size n minus 1 of the partition lambda where I have subtracted the corner. Okay? So for example, here, the corner, if the corner is this one, lambda minus c is just this partition when I have erased the corner. Okay? Okay, so what I say is that I can prove the formula if I prove this formula, if I prove that this is true. Okay, for NA lambda, I will prove that this is true. This equation is true. And this will prove the formula by induction on the number of, on n. Certainly the formula is true for n equal 1. You can check the Hooke formula for n equal 1, it's not difficult. Since you know it is true for n equal 1, then you can do induction on the size of the partition and you get, you want to check this formula, okay? Certainly the number of standard tableau of shape lambda, it satisfies this formula. Okay? It's clear that it satisfies this formula. So if I want to do induction on the size, I just need to check that this function psi satisfies this recursion. Okay, so how do you check that? Well, the proof is probabilistic because you rewrite it to write it as 1 equals the sum of some things. So I can rewrite it as 1 equal 1 over n, sum over c of psi of lambda over psi of lambda minus c. Okay? And now I will interpret these numbers. So maybe I could even put the 1 over n here. Now I will do the following. I will interpret these numbers as a probability measure by showing you a very nice stochastic process. So what does the stochastic process? What it does is the following. You take a random box in your partition. Say, I take a random box in my partition, say this one. Okay. So I call lambda this Young diagram. I take a random box. So one of them will be obtained with probability 1 over n, okay? And then I do the following. I look at the hook, which is here, and I choose a random box in the hook. Of course, I don't want to stay at the same place, so I choose another one, okay? The hook. Okay, maybe I take this one, okay? And then I do it again. I start from this point, I look for another point in the hook, etc. So at each time I move, and I can only move upward, okay, either in this direction or this direction. So in a finite time, after at most n steps, I will have stopped, okay? And where can I stop? I can stop only in a corner, okay? And what I claim 1 over n, psi of lambda over psi of lambda minus c, is a probability of getting c, so that c is the terminal state in my Markov chain. Okay, so this is a claim. So we have to check that. Okay, and if we check that, of course, since the sum of probability will be equal to 1, because we are with probability 1, we will get to a corner. And then we will get the formula is true by induction. Okay, so this formula is true, so the formula which is here is also true. So how do we check this? Well, okay, so so I need to look at this expression. It is a product. Okay, it's 1 over n times a product of. So let me draw a picture again. I'll draw a larger picture because it's okay, like that. So so my corner is here, say. So when I compute the hook length on the large diagram, and on a small diagram, I got the same thing except in the except here. Okay. Say okay on the top here on the numerator, I will get a 1 here that I can forget about, and I will get numbers here. So what are the differences? What I get is a product over ij which belong to the cohook of C. By cohook I mean the boxes whose hook end one of the end of the hook is in the box in the corner C. Okay. Now this is 1 over n, the product of 1 plus 1 over hij minus 1. So let me call, say, for example, A and B the coordinates of my corner. Okay. So this is 1 over n. I will expand this product sum over I1 ik j1 jk of 1 over a h I1 j1. So I will have the product. No, sorry. I made a mistake. So it's okay. So the hooks, there are these hooks we here and these hooks. So these hooks are there are some I A 1. So there is not necessary. Sorry, my formula was not correct. There is a K here, there is a L here when I expand. I expand over this product of boxes here and this product of boxes here. So I have, say, A1B minus 1 and a product, so the ASB, so product over S, and a product over T of 1 over A JT minus 1. Okay? Is it clear? No? Okay, I expand this product. Okay? When I expand this product, so I have a product over this here, which will give me a product of H A something with a subset of the J, which are a subset of these sets here. Set here, sorry. And I will have, so the J will be between 1 and B. And here, the I will be between 1 and A. Okay? Yes, order them, yes. Okay. I take the product of the hooks in the order, in these orders. Okay. And now what I claim. Okay, so if you see you have some points here which have been okay. My picture is not. I will make a even larger picture so you can see. It's better. Okay. So because what is really relevant is what happens in this. So here I have some shape. I really don't care what the shape is, but here I have A, B, okay, and I have some say J1. So no, I think it's I1. Yes, I1, I2, IK, and J1, J2, etc. up to JL. Okay. There is a certain number of indices that have been selected here and here, okay? And what I claim is that, again, there is a probabilistic interpretation of this product. What is the probabilistic interpretation?
To
Yes, okay. So what I claim is that, so I have a grid here, you see? So I can select a certain number of boxes, the one which are at the intersection here. Etc. Okay, so what I claim is that this number is a probability, the product which is here. The product times 1 over n, you're right, yes, times 1 over n. It's a probability. It is a probability that, that the Markov chain, X, has projections. So let me call I this set and J this set. Okay, my Markov chain, it will be a sequence of boxes, and I look at their coordinates, their first coordinate and their second coordinate. I say that the projections of the Markov chain are exactly as projections I and J. That means that the steps taken by the Markov chains, their first coordinate are given by some of the i's, and the second coordinates are given by some of the j's. This is what I claim. I prove it now.
So in particular, there are a binomial I plus j I of them.
Yeah, but because you expand 2 to something, it's just two sets of. Yes, I see. Okay, yeah, sorry, I see what you mean. Yes. Okay. So let me call this product P pi ij. Okay. So what I claim is that if this event takes place, then first I have to land on this point, the first one, because if I land on another point, then I will not get this to I1 or J1, I will be above. So certainly with probability 1 over n, X says the first step is equal to I1 J1. Okay? This happens with probability 1 over n. And then I will prove that this is true by induction on the length of I and J, of the size of I and J. So for this, I will prove that pi ij is equal to so my first step will be either this one or this one, if really my projections are these sets. Okay? So certainly I have to prove that this is equal to this plus this j. So say yes, comma j, I j minus j1, and I have to adapt. Okay, there is some hook length that I have to take care of.
Yeah, the probability that you are going exactly there or exactly there is 1 over root 1 is 1.
Yes. So it's 1 over it's this times 1 over h. Okay.
Minus 1 because you don't say P. Minus 1 because...
Yes, you're right. You're correct, yes. It's one of the terms which occurs here. Okay? And now I compare this product now for these two. I assume that by induction these two are given by my formula. And what I have to check is just that 1 over h so do I miss some? So what do I have to check?
But there are lots of factors. You lose a word column or a word row.
No, because no. I have.
Right. So
No, I don't lose many. I have, you see, I have all these factors here, and I have all these factors here in common. So what I lose is, so in the end, I get that, how is it? So I have to do the computation right. So I have to look at my paper because I want to make sure that I. Okay, so what I claim is that this is equal to Hij1 minus 1 plus Hi1b minus 1. Okay, this is just, huh? Yes, then I have to invert this, but essentially, this proves that you get this, you got plus this, and this is equal to this. Yes, and this is equal. That's right? No, sorry. This is, yes. Yes, no, it's this plus this, which is equal to this up to the loss of one box. Okay. Okay, and this, okay, so this should be equivalent to my quotient here, but I'm too tired now to check. But exercise for the next time, check that this is really this is really okay. But this is just this simple. So it is really this property of the hooks that really gives you the answer in this case. So you really have to check these probabilities that I'm correct. Okay, you have to check this when you lose. No, it's okay. It's okay. You see, you have just you have just two terms. You have just the two terms. One with the B on the left, and one with the B on the right, and one with the A on the left, which are missing. Okay, and you have two terms that are missing, and okay, so you divide everything by 1 over H A J1 minus 1, 1 over A n minus 1, etc. And okay, it works. I think it's finished. Okay. Well, thank you.